Okay, great. Thanks, Wolfgang, for the nice introduction, and also thanks, Chris, for the invitation. It's glad to be here. Chris is here. I've already had many exciting discussions, and I look forward to more in the rest of this day. So today I'll tell you a little bit about experiments that we're doing, trying to study many-body physics using superconducting quantum circuits, and in particular, thinking about what we can do if we couple these qubits to engineer baths. So let me motivate by saying that understanding strongly correlated quantum materials is one of the fundamental challenges in modern physics, but it is also of a great technological relevance. Examples include superconductors, quantum magnets, topological materials, so on and so forth. Now, many of these materials, we believe we have relatively simple models that capture their essential physics, but unfortunately, these quantum mechanical models are extremely difficult to calculate. And that's because these novel properties of quantum materials usually arise from the strong correlations or entanglements between the constituent particles. And that takes exponential resources to simulate on a classical computer. So that's where the idea of quantum simulation or synthetic quantum material, as people sometimes call them nowadays, coming, where Richard Feynman proposed this idea of trying to build engineered systems in the lab that can mimic the dynamics of another quantum mechanical system that you want to study. The purpose of building this engineered system is so that you can build it in a way that's very coherent and clean, that's dynamically tunable, and also easy to probe the physics that's happening in these new quantum systems. And I want to emphasize that even though they're called quantum simulators, you can do more than just simulate existing materials or existing systems in nature. These systems allows you to go to parameter regimes that are also not accessible in everyday life. By now, there are many different experimental platforms in which people are building these quantum simulators or synthetic quantum matter, cold atoms, trapped ions, and other systems. And we have a few research labs here locally that are exploring these physics as well. Let me just give you one example, right, of this quantum simulation. If you think about in real materials, on the left-hand side, you have electrons that are moving around in the lattice potential formed by the positively charged nucleus, and they are interacting with each other. And this gives you all kinds of interesting quantum phases. Now, if you switch to ultra-cold atoms, what you can do is you can build these quantum simulators where you put individual laser-cooled atoms into a lattice potential that's now created by interfering laser beams. So now instead of electrons in solids, you have individual atoms in an optical lattice where you can now simulate different quantum phases and also look at, for example, the individual positions and properties in a way that you can't access in the real material. Now, in today's talk, I'm going to show you how we build these quantum simulators and do interesting physics using microwave photons as the particles. So imagine you're going to have arrays of superconducting qubits or superconducting resonators in which you have individual microwave photons that are moving around and interacting. Okay. I'm just going to give you a few examples of the kind of systems that people can build. And later on, I will dive into details of how we build one such system and how does it actually work in detail. But for now, for example, this is a lattice that you can build from coupled microwave resonators. This is one of the early review papers on using superconducting circuits for quantum simulation. And you can see these resonators act as lattice sites for microwave photons. And in this case, they're arranged in a Kagome lattice, which is of relevance in many quantum materials, superconductors, and quantum magnets. This is one example where it's of relevance for material physics, for example. But making use of the fact that these resonators are just lithographically defined, and you can pretty much route them however you want and couple them in many different ways, you can use now these superconducting circuits to also build lattice models that don't exist in nature. So this middle example is a hyperbolic lattice living on a curved space, which can be used, for example, to represent the space of an expanding universe. Now, these two examples so far, they are just classical resonators. You can cool them down in the dilution fridge. The metal, the superconductors, in this case, can go superconducting, and you have microwave photons that can live for a long time. But to access many of the interesting many-body physics, you also need interactions between the microwave photons. And that's, as I will show you later, we do by coupling these lattices to superconducting circuits, or to directly build lattices out of superconducting qubits, which are now these interacting lattice sites for microwave photons. Now, assume that we already have these flexible ways to build interesting models for quantum simulation. The question I want to address, or at least show you some of our aspects, is to ask, how do you now prepare interesting many-body phases, right? You only have this empty lattice. Yes, exactly. So in this case, here, so each of this meandering line is actually one microwave resonator. You can now think of it as a lattice site. And for example, this picture here shows where three resonators meet. So that's how the nearest neighbor coupling is built. And you can now see this weird thing with these. So normally you think of lattice sites as these point-like objects, and your connections as these lines. But in this case, the lattice sites are these distributed objects, but your connection is local. And that's actually how they use that to generate this curve, lattice on the curved space. Yeah. So in this case, it's in this case of fractional quantum Hall physics, there is a synthetic gauge field created by having a tunneling phase when the particle moves around one placket of the lattice. So that is by engineering essentially a phase in the tunneling, in the coupling. Yes. 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 So yes. So the microwave photons in this lattice are essentially modes in this resonator. So what's happening here is the three little solid black lines you see are little gaps in the metal. So they are parallel capacitors, which capacitively couples nearest neighbor resonators. So the microwave photon on one lattice site or one resonator can tunnel coherently to its neighbor. In the C panel still. So they're just so that your resonators are not shorted to the ground, because the outside white is the ground plane. Yes. Yeah. Yes, please.
So if your capacitance control you have over the individual tunneling strengths between.
Correct.
Are you sites, or how does the routing work?
Yeah. So it gets complicated, but certainly you can think of having beyond nearest neighbor coupling. You can also think of using this routing to do weird boundary conditions. For example, you can actually route the two edges of the lattice and connect them together. And there are also other ways. For example, you can couple this whole lattice to a microwave resonator that's common on top to mediate, for example, long-range interactions. Now, the question about what rates you can get, right? In this case, you can see that the coupling rates will be fixed. It's just how much capacitance you design. In more, let's say, some of these qubit-based architectures, then it's also pretty standard nowadays to have a coupler circuit that is tunable. So you can have a tunable coupling. All right, great. OK, so talking about building lattice is one thing, and then putting particles in and creating the right states or the right dynamics is a different story. Especially thinking about these microwave photons, they have some intrinsic loss, right? So I want to take kind of some motivation from what we do every day in condensed matter. In condensed matter, if you have a piece of superconductor, the way you get to superconducting states or other quantum phases is just by cooling it down, attaching it to the fridge, or attaching some electrodes. This we kind of do for granted, right? And how we actually reach these quantum states, how that system interacts with the bath, is usually hidden, and we don't have direct access to the microscopic details of that process. So here, we're taking that as a motivation to ask, in our quantum simulators, can we also use reservoir engineering or bath engineering to, for example, induce and probe dynamics and different quantum phases in our superconducting circuit lattice? Can we use this bath engineering as a tool to generate and also manipulate correlations and entanglements, just like what we're already doing naturally in real materials without a lot of insights? And then finally, we can think about using this both to answer fundamental questions in open quantum systems, but also to use these correlations and entanglements as applications or as resources for quantum information science applications. Okay, so this is kind of the big picture, and I want to hopefully show you some of our initial experiments going along that direction. This is a quick outline. I'm going to show you how we actually built a Bose-Hubbard lattice using these arrays of superconducting qubits. I'll show you one way how we're building these engineered baths that will serve as sources and drains for particles, which again are these microwave photons. I'll hopefully have time to show you two experiments. One in which we couple these source and drain to our lattice and induce out of equilibrium dynamics, transport dynamics through this lattice, which we can then probe in situ. In another example, which I'll probably go over pretty quickly, I'll show you how we can use the same reservoirs as tunneling probes to perform tunneling spectroscopy on our synthetic lattice. I might have a minute or two in the end to show you how these tools also tie into our other ongoing efforts to then not only probe the system, but as I mentioned before, to actually generate entanglement and correlations. And also, since we're talking so much about bath engineering and reservoir engineering, it's natural to ask, what are different ways to characterize the kind of decoherence or dissipation you have in the system, and eventually maybe to use them as ways to change or probe the quantum state. Okay, so the lattice we're going to implement here is the Bose-Hubbard lattice. It only has two simple terms in this system. So you have, in this case, bosonic particles, because our microwave photons are bosonic. So a particle on one lattice site in this periodic lattice has a rate to tunnel to its neighbor with this tunneling rate J. And whenever you have two particles on the same lattice site, they have interaction energy of U. Okay? And of course, you can imagine that each lattice site may not be at the same energy, so you can put in also a local offset. The Fermi-Hubbard model, for example, we believe to capture the essential physics of high TC superconductivity. Here we have a bosonic system. The bosonic Bose-Hubbard lattice has two ground state quantum phases. If the tunneling is large compared to the interaction, you have a superfluid phase. And if the interaction is strong, you have an insulating phase that we call the Mach insulator. And there can be essentially a metal to insulator transition happening as you tune these parameters. Okay, this is our device fabricated in-house at Purdue. So here in the middle of this device is this array of, in this case, only 4 coupled superconducting qubits. And this realizes a 4-site Bose-Hubbard lattice. Now, let me walk you through. So each of these cross-shaped is essentially a LC resonator for microwave photons, but it's a nonlinear LC resonator. The cross that you see, this light gray, is a superconductor patterned on an insulating substrate. So this cross you see is a capacitor to ground the surrounding. And on the bottom of this capacitor is a Josephson junction, which for the purpose of this talk is just a nonlinear inductor. Okay, so you have a capacitor and a nonlinear inductor, which makes you this LC resonator. Now, why is it important to be nonlinear? If you just have a linear LC resonator, then you have a harmonic trap, and you can put in as many photons as you want, and they will all be at the same exact energy. Okay? But here we want the photons to interact and to feel each other, right? So this U term here. So by using a nonlinear resonator, what it means is, for example, if the first photon I put into this circuit has a frequency of 5 gigahertz, the second one, because of the nonlinear spectrum, would be at a very different energy, for example, 4.7. So this change, or this difference in energy between the first photon and the second photon becomes our effective interaction, right? Because they feel each other energetically. Here, I'm glossing over this detail that instead of one Josephson junction, we're actually using 2 connecting in parallel. This forms a squid loop. And the reason we have this is by putting a little magnetic current, a little current next to the squid loop, you can change the effective inductance of this squid loop, and thereby changing this on-site frequency epsilon here. So now the only piece left is to have this nearest neighbor tunneling J. We already covered this, right? So one simple way is just by having a capacitive coupling between nearest neighbor qubits. So in our case, this tunneling is fixed, and you can change it by changing the capacitance, and we here have it on the order of tens of megahertz. Yes? So it's not explicit, so it's just some residual capacitance between these 2 cross-shaped things. Yeah, the fact that they're close, exactly. And that's how we control it as well. Exactly, yes. Yeah, exactly, yes. Just to show you what else do we have on this device. So on the bottom, these traces, they go next to the squid loop. That's where we send in the little current to change the individual on-site frequencies in the lattice. On the top, you have these meandering lines. These are now similar to the resonator array you saw before. So these are microwave resonators that are coupled off-resonantly to the qubits that we use for readout. So you can see they're all coupled to this common transmission line, which we send microwave photons in. And the way these readouts work is the so-called dispersive readout. So the frequency of the readout resonators, as it turns out, varies slightly based on how many photons you have on the particular lattice site. Okay, so this is a photon number dependent frequency shift on the readout resonators. And by having this common transmission line, we can do frequency multiplex readouts, so we can read out the states of all of the individual lattice sites at the same time. Some numbers for this particular device, the on-site interaction, 250 megahertz, is much larger than the nearest neighbor tunneling on purpose. So you are in this very strongly interacting Bose-Hubbard lattice. The single particle loss, which is essentially the lifetime of each of these transmont qubits, is about 30 microseconds, which in line with is about 5 kilohertz. So you can see this starts as a very coherent lattice where a particle can tunnel thousands of times before it's lost. And dephasing and disorder is a little bit worse due to technical noise, but still small compared to both the tunneling and the interaction. Okay. Okay, so starting with the strongly interacting coherent lattice, the next step is to add these engineer baths, please. Yes. I will show you in a few slides what we're accessing. So you can see in this case, we have fixed U and J. But what we can do in the end is we can vary the chemical potential or the density. So we can actually see a density-induced transition between superfluids and Mott insulators. Correct. We can have multiple Mott states with different fillings. We can have these strongly correlated superfluids. Very good question, right? So this is one of the challenges. If you don't have particle number conservation, or if you have intrinsic loss, how are you going to prepare these states? And the bath engineering is kind of along that direction. Now, here, it's certainly true that it's pretty coherent to begin with. So within a short amount of time, you can still treat this as a particle number conserving system. But if you're thinking about longer times or larger systems, we are exactly going to use the engineered bath or the reservoirs as a way to populate this lattice, maybe even in the presence of dissipation, right? Yeah. To stabilize the many-body states in a way. Okay. Bath engineering. I think if you look on this chip, this is a very standard coupled superconducting qubit device. And we ask, where do we already have dissipation? Right? I already mentioned that we have these readout resonators. And of course, the readout resonators are coupled to the environment because that's how we do readouts. So we're actually just going to use the readout resonators as our source of dissipation for these engineered baths. They are originally designed to not really affect the coherent dynamics in the lattice, but now we're going to actually actively couple them resonantly to the qubits. There are two processes that we can employ. So a little bit of details. So you have this qubit latticite here. So we're just taking one latticite as an example. And you have a readout resonator that's just a harmonic trap that's far detuned with some coupling G. And this readout resonator has a line width, okay, that we normally use for readouts. So we use two parametric processes to build either a particle source or particle drain. This first process, what we do is we actually modulate the on-site frequency at a frequency that's the difference between the resonator frequency, omega r, and the qubit frequency. This puts sidebands on the particle in the lattice so that the particle sometimes lives at the frequency of the resonator. So you've now parametrically turned down a resonant interaction that allows particles in the lattice to resonantly leak out of the system through this resonator. Okay? So you can see in this example, if we start with one particle in the latticite, we turn on this bath interaction, and you can see it quickly decays to the ground state and will leave there as long as your bath coupling is on. Okay? Another process to now have a particle source. So the way we do this is now we modulate the qubit frequency at the sum of the resonator and the qubit frequencies. So this modulation itself is a coherent two-photon process that puts one particle into the lattice, one particle in the resonator. But because the resonator is lossy, that photon is just gone. So you've now turned this coherent pump into an incoherent process where you only unidirectionally add particles into the lattice. Okay? And you can see here in this data where we start in the ground states, as this bath is turned on, you go to the excited states, and it stays there even though you have intrinsic decay. Okay. Let me skip the numbers. Just point out that these are tunable local baths. How strongly they are coupled to the lattice is just how strongly you modulate. And at what effective detuning your particle source and drain are is just the effective detuning of the modulation frequency from these resonant conditions that I have here. Okay. All right, so moving on. Yes? Yes. Yes. Correct. Yes. Yes. Exactly. So this modulation is basically a small modulation signal that we send in from this bottom port, which changes the on-site frequency. Yes. Yes. So yeah. So you can see the, okay, so these are the resonant conditions, right? Which corresponds, for example, in this case, a particle resonantly leaking out to this effective bath with line with kappa and some effective coupling. So if I change this modulation frequency, you can essentially think of this bath being moved up or down in detuning in frequency, right? And the strength of the coupling, the strength of the modulation is what changes this coupling, this effective coupling. Because it's how strong the sidebands are, how much population of the qubit is put into that. Yes, correct, exactly, yes. This is, I hope at this point, at least this cartoonish picture is clear. We have a coherent lattice. We can have these tunable local source and drain. And if you attach them at the two ends, you're going to be doing a transport measurement through this interaction channel. Okay. Let me give you a very quick, okay, so there's one thing that's missing, so which is how do we measure this current, right? So in this case, you actually can have a steady state current. And normally you think of measuring current in these synthetic quantum matter by looking at how density changes, right? But here, if you have a steady state current, density isn't going to change. So we have a way to measure the currents in situ. And the way we do that is to do something like this. So imagine at some point you have a many-body state, and there's some current, which is particle current. So there's some motion of the particles across these two middle sides, okay? So mathematically, you can write this pretty simply. It's basically creating, destroying one particle on one lattice side and moving it onto the neighbor, okay? And then there is the opposite process. There is a J tunneling in here because that's how fast the particles are moving. The way we measure this is actually using a trick where we map the current to density, okay? Because density is what we measure eventually with these readout resonators. It turns out if you isolate these two middle sides, just these two middle sides, while keeping the tunneling on, and you wait a quarter of the period of the tunneling, you map current to density. If you want an analogy, think about a harmonic trap. Wave function in a harmonic trap, a quarter period maps position to momentum and momentum to position. And this is very similar. Okay. Some little additional caveats, which I'm going to skip. One is that we have a strongly interacting system, so there need to be some small modifications in the scheme. And the other thing I want to point out is this mapping from here. You can see that the current actually also should have discrete eigenvalues, right? Which are integer multiples because this n difference times j. But the upshot here is we have a way by measuring on-site population in the lattice after this beam splitter operation, after this tunneling, which allows us to directly extract the in-situ current, not only the expectation value of the current, but also quantum fluctuations in the current. Okay. In the interest of time, I'm just going to stop there. Okay. So this is the setup that we want to cover, right? So bath-coupled transports in this Bose-Hubbard lattice. And the experiments I'm going to show you, we will keep the source and drain at the same energy, okay? And move them up and down together with respect to the lattice. And we're going to measure the steady state, or measure the currents by measuring, for example, the link at the middle of the lattice. Here is where I probably should point out the numbers. So kappa, if you remember, is the bandwidth of these particle source and drain. Okay, these are narrow bands particle source and drain instead of your typical chemical potential that you think of in a fermionic system. So that line width is about 1.5 megahertz. The tunneling in the lattice is about 6 megahertz. And for this particular set of experiments, we're going to stay in the so-called hardcore boson limits because our interaction is so much larger. So think of it in the case where you can have at most one particle per site, okay, just for this particular experiment. Okay, so on the x-axis is the bath detuning between the bath and the lattice, okay, and the two are moving together. On the vertical axis is the measured steady state current, and I'll show you what we mean by steady state. This blue curve is when the bath, both the source and the drain, are coupled to the lattice with a coupling that's relatively weak, about 1 megahertz. You see that there are 4 distinct locations where you see some steady state currents. I'll show you in a minute that these corresponds to transport through the discrete conduction channels that corresponds to the single particle eigenstates in the lattice. Okay, we have 4-side lattice, the single particle quasi-momentum states, there are 4 of them. We then turn on the same experiments, but now with a larger coupling between the bath and the lattice, so the particles can enter and leave the system faster. You can see now you still have the same 4 peaks as before, but there is a higher current. In addition, you have these additional features. As you will see, these are actually now interaction-induced transports where the source and the drain can actually provide 2 particles at a time. Okay, so these are interaction-driven nonlinear transport. Let me first show you the same. So this is the same data on the right-hand side, but now showing you actually the dynamics of this current. Okay, so for example, this data here, this data here is picking this particular detuning of this blue arrow, okay, and showing you after the source and drain are turned on, how does the current change as a function of time. You can see it starts at 0. There's some initial transient dynamics, then it levels off and reaches this quote-unquote steady state in about 1 to 2 microseconds, which seems to be consistent with these bath coupling rates of 1 or 2 megahertz. Okay. Just for fun here, what we can do is we can actually abruptly turn off the 2 baths. Okay. So now you have a many-body state that has some finite momentum, which is now evolving again in this closed coherent lattice. And what you see is the particles essentially bouncing back and forth in this lattice if you want. And as a result, you also see these coherent oscillations in the current. Let me come back and point out where these 4 peaks correspond to, because this might come in handy later on. So here I'm plotting the many-body spectrum of this lattice in the hardcore limits. So in the hardcore limits, we can only have at most 1 particle per site. So the states are labeled with total particle number on the x-axis. So you can see this is the vacuum states. These are the 4 states with 1 particle. And all the way to the right is the 4 particle states. Okay? So you can see these 4 little peaks in the blue curve actually correspond to transports primarily through one of these 4 single particle eigenstates. And if you look at the spectrum, you can also see that the additional peaks here corresponds to processes where you can populate 2 particle eigenstates and doing transport through that. Okay? And this is only possible because the particles in this lattice are actually strongly interacting. Otherwise, you wouldn't be able to put in particles at this off-resonant energy. Quick note here, I'm not going to dive into, is if you think about what a current is, actually current corresponds to some coherent superposition, or some coherent motion of the particles. So this naive picture of just populating one particular eigenstate is actually wrong. Okay, so the fact that we see a coherent current means that there is some some complicated interplay between the coherent lattice dynamics and the dissipation, such that you are stabilizing some many-body states that has coherent superpositions between different states. Okay, I'm going to leave you with one small puzzle. Hopefully, some of you can pick it up and help me figure it out. Have we really reached the steady state? By looking at the currents, we certainly have. We also measure the total particle number in the lattice. And you can see, actually, the particle number within that same time scale is still growing. Okay, the thin line is the numerics. So if we do the numerics for longer and look at this time scale on the x-axis, you can see, actually, it takes almost an order of magnitude longer to reach the true non-equilibrium steady state in the lattice. While the current, which is some dynamical property, coherent property, has leveled off much early on, okay? And the weird thing here, at least to me, is if you look at the contribution from the different states with different particle number, okay? If you look at the particle number, okay, the total particle number, you can see your state is still evolving, okay? You are going slowly towards states with more and more particles. And if you look at the current, and here there is a little detail I should point out. Current is a measure of the motion of the particles, so the current doesn't change particle number by itself, okay? So that means when you measure the total current, which is this back line, you can actually measure the contribution of the currents from each manifold of states with different particle number. If you plot those, you can see that the many-body state indeed is still evolving quite drastically over this much longer time scale. But somehow the total currents seem to have reached the steady state at much earlier times, okay? Okay, well, in the interest of time, let me just quickly tell you what we want to do with these techniques. So we have a way to measure local currents using these source and drain. And the goal is to then apply these to these much larger, more complex lattices, right? So for example, we have one experiment ongoing with a triangular ladder where we can explore the interplay, the crossover, for example, between 1D and 2D physics. This is also where we can explore things like frustration and synthetic gauge fields. And you can try to think about topological lattices where, for example, you can look at not only the steady state, not only the local currents, but also, for example, current correlations. Something I didn't even mention here is we not only measure currents, but also the fluctuations in the currents. And if you're coming from a condensed matter background, this is analogous to, for example, short noise measurements that you do. These fluctuations, quantum fluctuations in the currents tells you something about the underlying phases. Okay. Next thing, which I'll spend not too long, hopefully, on, is to think about doing spectroscopy, tunneling spectroscopy with these baths. I think again, the physics, the cartoonish picture is probably clear at this point, right? We have these particle source and drain that we can attach locally to the lattice. And we can use that because these particle source and drain are narrow bands to probe the spectrum of the many-body system. Well, STM, STS, so scanning tunneling microscope, scanning tunneling spectroscopy. These are some of the most powerful tools that we have for probing the microscopic dynamics, the microscopic properties of quantum materials. And here we're doing this with our system, right? So imagine you have on the right-hand side some many-body system with some local density of states at different energies. The state is filled up to some chemical potential. And now, if you couple them to a narrow band drain, you'll be able to probe at what energies you have states that are filled, right? And if you couple them to a source, with the narrow band and tune this around, you'll be able to probe by looking at how much tunnel current there is, at what states do you have empty states. Okay. In this quick example, this is a kind of almost a trivial example where we start with an empty lattice, okay, and we have this narrow band path coupled to the first lattice side, okay, and as a function of the detuning of this probe, and we measure how does the population in the whole lattice change as a function of the probe duration during which the probe is coupled to the lattice. So in this case, we're going back to the case where the lattice itself is a closed system, okay? So assuming that the only way the particles change, the particle number change is via the path. So you can see the same, in the same level diagram as before, right? We're starting from this ground state, the vacuum, and now we're probing at what energies can you put a particle into the system. And you see these 4 different peaks, which corresponds to the single particle eigenstates, or the quasi-momentum states of the lattice, if you want, in this 4-side lattice, okay? And from that change in the particle number, we can extract the spectrum, and you can see it actually matches with what you calculated for this many-body system very accurately. With the way we implemented our path, which we're now using as tunneling probe, you can imagine doing a scanning tunneling spectroscopy because we can turn on this probe at any location in the lattice, right? So this, for example, what allows you to probe the local spectrum as a function of position, which is useful, for example, if you have fragmentation or localization in the lattice. This is another simple case. So here, I just want to show you quickly that, okay, so let me go back. So this is a particle excitation, right? We're using this particle source to only probe energies where you can put a particle. But you can use this particle drain to now probe at what energies you can take out a particle, meaning which are the occupied states. So in this case, we start with this so-called Mach insulator state, 1 particle per side. And we couple the first side to this drain, okay? So now you're starting with this state here and looking at what energy can you take out 1 particle or create a hole, if that's the language you prefer. Same thing, okay, in this hardcore boson limit, you have this particle hole symmetry. So a single hole on top of the Mach insulator looks just like a single particle in the empty lattice, okay? Okay, so this is coming back to Smitha's question before of what states can we prepare in this Bose-Hubbard system? And in this case, I'm gonna show you in the context of doing the spectroscopy, okay? So the 2 states I've already shown you is the vacuum state, where you only have the 4 particle excitations, right? And the Mach insulator state with 1 particle per side, which in the ground bands, you can only take out particles. You can't put in particles anymore, okay? We actually have a way to coherently prepare the lattice at different densities to go through this phase transition, this part of the phase diagram, okay? So we can actually, for example, prepare these states with 1, 2, and 3 particles in the whole lattice. You can see these are now superfluid states where you have both quasi-particle and quasi-hole excitations in the ground band that are low-lying energy. You can also see that there is this asymmetry between the hole and the particles, partly because this is a strongly interacting system, and partly because you can see while we change the density, we're essentially changing the chemical potential, okay? So you can see where the particle and the whole spectrum kind of meet is where the effective chemical potential is, okay? Now, for this Mach state, this Mach insulating state, it's an insulator because compared to these superfluid states here, they have close, low-lying particle and hole excitations. I'll get back to right away. But for this insulating state, because you already start with one particle per site, now to excite anything on top, you have to pay this large energy of U, okay? And this we see by probing higher frequencies, right? You can see for the small states, n equals to 1, the hole excitations are all here, and then all the particle excitations are up here with a gap that's U. And this tells you from the spectroscopy the change in the many-body gap.
Have like particle spectra, or the common phase, or the different.
We probably do, and this is one of the things that we are actually exploring when we go to these systems that involves higher levels. Correct, yes. Okay, other things I can quickly show in the same spectrum. So, again, going up from n equals to 4, you now have, again, superfluid, which is the superfluid in between these two Mott lobes, right? So again, you can see there is this, both the particle and hole excitations. You can also see that the spread of these states excitations are now wider, and that's because now you have particles tunneling on top of the n equals to 1 Mott insulator, and your tunneling has this effective bosonic enhancement. Another thing we can do is at some point, you're going to start to have 3 particles on the same site, okay, in these excitations. And now, normally, if the way I describe it, we have 2 particle interaction U. So once I put the 3rd particle, I expect that excitation to have to take energy of 2 times U, right? There are already 2, and I have 2 pairs of interactions I have to add. These excitations are here, but if you look at this axis, 2 times U is actually here, shifted to one side, okay? So the fact that these 3 particle excitations are shifted is because we're actually seeing the effective 3-body interaction, okay? And I'm just going to stop here, but mention that we actually have ways, or we're working on experiments, where we can effectively turn off the 2-body interaction, leaving only a dominant 3-body interaction. And this is one place where you can have exotic many-body phases, for example, those with density wave order. Okay, so the clock is a little slow, so I'm gonna just spend 2 minutes giving you a quick outlook and some of the things related that we're working on. I mentioned most of the experiments I showed you focused on using these engineered baths as a way to probe the system, okay? But the other side of it is to use these baths to actually prepare and manipulate many-body states, just like how we do them in condensed matter, right? So we have one thing that we've been doing is to use these driven-dissipative baths, sometimes in addition to the coherent control that we already have, to think about how can we design correlations and entanglements that are robust to intrinsic decays in the system. How do you stabilize those entanglements? You can think about, where do you put these baths? What frequency do you want to do? And you can also think about dynamical processes versus steady state. You can also go from local baths, which is what I've only showed you today, to non-local baths, which can, for example, give you new opportunities for generating long-range entanglements. And of course, the extreme limit of this is the limit of cavity QED, where you have a cavity that couples to all of the qubits, which is something we're excited to try as well. The other thing, which might seem a little disjoint at this point, is we are thinking about using these engineered baths to do many-body physics, right? But of course, we do already have intrinsic decay or intrinsic decoherence in the system. So to do that efficiently, we probably also want to figure out what are these intrinsic dissipation. So we're working on, let me show you everything. We're working on, for example, general ways to understand many-body decoherence, including multipartite relaxation. And something that we already saw in our experiments is actually we can see collective decay when you have excitations that are delocalized over the whole lattice. You can ask me if there was time, but I think this has been a recurring theme in this iQuiz series. You've heard many talks in different experimental platforms of superradiance, subradiance, collective decay, and things like that. Okay, finally, I just want to end on this slide. This picture of this Kagome lattice this device was shown more than 10 years ago. We haven't really gotten the point where we actually do quantum simulation with a lattice of this size. Both the local control of the coherent dynamics, but also just how we actually are going to control and probe this many-body system. So I hope the experiments I'm showing you today is kind of our efforts towards that direction. Can we use these baths, for example, and other tools to one day be able to do these large-scale useful quantum simulation in superconducting circuits? With this, this is the team that did the work. In particular, I want to point out Purdue, who is my senior graduate student, who is really the one pushing most of these experiments. He's graduating next summer, so that's an advertisement for the PIs here. And of course, I'm looking for postdocs and people to join. Thank you so much.
So we have 4 minutes. We'll take a couple of questions. I know there was a couple, or there was a lot during the talk. We'll get time for one or two more. Yes, we will.
So in this case, you can see the transient dies off in about a microsecond, which is similar to the bandwidth of the bath and also the coupling rate between the bath and lattice. So it seems that maybe that time scale is related just to how fast the particles can enter or leave the lattice. Yeah. At least that's kind of qualitatively what we see. Yes, please.
You have shown a way to tune the, for example, the loss or the gain of the system, and I believe there is a mature way to demonstrate the modulation of the coupling between the sides. Is there a way to modulate the interaction of this qubit in the in-situ?
Yeah. So in one is you could in principle think about designing different qubits that have different interactions. In this particular architecture, the U is fixed by design, but I mentioned we're exploring this way to turn off U effectively. And the way we do that is actually via modulation-assisted tunneling. So again, as you said, basically you can think of some ways to modulate the onside frequency such that you offset the energy it would normally take to put in a second particle. Yes.
So photons are bosons?
Yes.
Is there any thought to sort of make bosons like fermions and sort of expand effective simulation?
Okay. So if you're a condensed matter physicist, the answer is no, not easily. So it's hard to actually directly, natively implement this fermionic system. Now, these are, of course, these map naturally to spin models, right? So there are different ways to engineer spin models. If you think that's kind of away from bosonic system, that's one way. Two is, in fact, in this 1D case, because they're so strongly interacting, you're actually in this so-called Planck-Chaudhuri gas limits, where the bosons in many ways behave like fermions. So there are still interesting regimes or models, I think, that we can access, even though these are bosons. Yeah. And you can, of course, think about other things where, for example, you couple a two-level qubit as a spin to a bath of bosonic modes, right? And that's also something that people are interested in condensed matter. Yeah.
Please join Alex for lunch upstairs.